Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. Today we're actually going to be looking at predicate logic, and we'll be looking at how to prove an argument as being invalid, or in other words, looking at invalidity. You're going to see in this video, we're going to cover two methods for looking at invalidity. The one is the counterexample method, and the other here is the finite universe method. So, welcome back, guys. I hope you're doing well. Today we're going to be looking at the question of how to prove an argument invalid. And just to remind ourselves, just to go back here, in terms of sort of kind of a brief review, an important thing to remember is that the sort of deductive proofs we're giving obviously don't prove validity. So they don't prove invalidity, right? Again, let's sort of review here. What is an invalid argument, or what counts as an invalid argument? An invalid argument is an argument in which it is possible to have true premises, I should say all true premises, and a false conclusion. So that's what an invalid argument is, where essentially these are all of your premises. Imagine that I have all of these different premises, and then I have the conclusion. The conclusion will be false while each of the premises is true, right? And that's what makes an argument invalid. Now, the difficulty when we look at on how to prove invalid arguments is the idea that in predicate logic, we haven't gone over how to use these. And you'll recall that when we looked at normal propositional logic, we used a method called the indirect truth table method. And we're going to sort of see today that the finite universe method utilizes utilizes a form of the indirect truth table method, but it's not as simple as it sounds. So we're going to sort of hone in on that. So if you haven't seen it yet, watch our video on the indirect truth table method first prior to watching this video. Or as well, we've also had a video on the counterexample method. This is from chapter 1. Take a look at that. We're going to be reviewing that now. So let's get into today's session, in which there's two methods for proving an argument as being invalid in predicate logic. The first method here is the counterexample method. And the counterexample method essentially meant that first we symbolized an argument, then we tried to come up with a substitution instance in which you would have all true premises and a false conclusion. And if we could come up with an argument that ultimately was obviously untrue, then we could prove an argument invalid. The other method here, and we're going to start a video by talking about this thing, but the other method here that we're going to learn about today, and actually it's much more complicated, but more promising, I suppose, is the finite universe method. And I'm not going to try to explain that yet. I want to sort of go over the counterexample method. But these are the two methods we're going to be taking a look at today. You'll see that neither one of them makes it very easy, actually. The finite universe method ultimately is the best method. It's better than the counterexample method, I think. But neither one of these is easy. So let's sort of just kind of talk about the counterexample method to start with. And we can sort of ignore the finite universe method for now. So what exactly is the counterexample method, right? Well, essentially, to remind yourself, it takes three different steps. The first is to symbolize your argument. Symbolize the argument form. Now, that's not too difficult because most of the problems you get, we're going to give you the symbolic form to begin with if you're going to do a counterexample method. But first, the basic step is to symbolize the argument form, right? Two is then to essentially, in terms of predicate logic, what we're going to do is we're going to then put it in ordinary language. Now that sort of goes, you can see here that the counterexample method, this one, if you already have the symbolic form, then you're going to put it in ordinary language. If you're going to symbolize it, you may be starting with the ordinary language and then symbolizing. So these two things can be probably reversed, maybe. It depends on the sort of argument you're looking at. Most of the homework books we have are going to have an argument form, so you're going to put it in ordinary language. And then three, then you're going to look for a substitution instance. right, that demonstrates invalidity, which means the substitution instance where all of the premises essentially are true, and the conclusion is obviously false in the substitution instance. Um, that fits invalidity. So let me do a couple of examples here, just so you can see what we're talking about here. Whoops, I misspelled that, didn't I? Let's fix that. I can't stand leaving a spelling mistake out there. Invalidity. Okay. So and then if you find that, then it's invalid. The difficult thing in this method is it's very difficult to sometimes find a counterexample. But let's just give an example here, just so you can see what it looks like. Let's imagine we had this example here in predicate logic, where we had this. Actually, before I want to make it on a larger. Okay, let me just I want to make a very large file here real fast, because we're going to be running through quite a few problems here. So I'll probably go ahead and try to cut that out when I can. Okay, so let's start with the example here of the counterexample method. And here's what our problem looks like. We have a particular claim as the first premise, EX, and then we have AX and not BX. The second premise here is all C or B, which is going to look like this, CX, then BX. The thing to remember here is that when you see the conjunction here, this is a sum A or not B, and this is an all C or B statement. And the conclusion we're looking for is EX, CX, and not AX. Okay, so let's begin by translating these statements. Now, again, take a look at our first video, 8.1, in which we talk about how to translate these statements. But what would this statement say here? This statement basically says that sum A or not B. It's a categorical claim because it has a quantifier. So sum A are not B. And then what is this one, the next premise, going to look like here? This premise is going to say that all, because this is a universal quantifier, so this says all C or B. All right, and finally, let's write in the conclusion. The conclusion here says what? The conclusion says this is an existential quantifier, so it is a particular claim. So that means I'm going to need the word sum in there. Some C are, and this says and not. That basically means are not. So that's some C or not A. And this is a simple example, but this is sort of how you do the counterexample method. And then what you'd want to do is then find a substitution instance for the A, the B, and the C, in which my premises here are going to be true, but all of the premises have to be true, and the conclusion is false. Okay? Now, so an important thing to remember here is that's the only thing we're testing for, true premises and a false conclusion. We are not looking to see if you have true premises and a true conclusion. In fact, if we did come up with a substitution instance in which all the premises and the conclusion is true, that proves nothing. It doesn't prove the argument valid, and it doesn't prove the argument invalid. Okay, it's possible, again, for an invalid argument to have a true conclusion. And so this is something that oftentimes I think people sort of forget and or get lost on, but that's a really important element. Okay, so what could we do here? Well, let's imagine, oftentimes, one of the things to remember is if you're using the counterexample method, right, you have to use examples that everyone agrees with. Or at least examples that everyone will recognize as either true or false. And the reason that's important is because if you use an example here in which people actually don't know if that's true, then that substitution instance doesn't prove anything, okay? So it has to be something that we all agree on. Now that actually represents a sort of problem in logic, which is namely logic fundamentally, in order to prove anything, I shouldn't say that, but logic fundamentally is divided in terms of our experience and doesn't care about your experience. So what that means is that you have to use examples that pretty much everyone understands. Using categories like animals and cats and names of animals, that seems to be a good way to go, because most people, there's pretty much universal agreement on these sorts of things, on who counts as a mammal and who counts as a reptile and so on and so forth. So let's start with this one. Let's say, and remember, these have to be true premises, and obviously false conclusion here. So let's imagine this first premise says that some animals are not mammals. So let's write that in here as what we're going to do. Animals. And then B is going to be mammals. Some animals are not mammals. That's true, because some animals are reptiles. So B here is mammals. Now A is animals, so I can put that down here in the conclusion. So what should C be? I need to come up with something that's true in this statement, something that's false in this statement. What if we made C cats, right? All cats are mammals, therefore some cats are not animals. So that's obviously false, and that's obviously true. So cats works great here as a substitution instance, right? Because think about this statement. Some animals are not mammals, that's true. All cats are mammals, that's true. Therefore some cats are not animals, that's false, which means that this argument must be invalid. Now, you can use the substitution instance here. Of course, the difficulty, though, is finding examples that work with you, and you'll see that the more complicated the argument, the more difficult it becomes. Let me do one more problem here with the counterexample method, just so you can see it in operation here. And again, for these examples, I encourage you to actually write down the problem, pause the video, and then sort of come back and see if we came up with the same thing here. Okay. Now you can see here this example uses a universal claim, but then these are not universal statements, right? These are not categorical statements. So that has to be reflected in the counterexample, and that's why I want to do the ordinary language here. So what would this first premise look like? Well, it really says all A or B is what it says here. Okay. All A or B. Now, what does this claim mean? This isn't talking about all of the A's. It's talking about just one member, one actual name, because this is what we would call it, a name here that's been given to this predicate. So this could be a Charlie, A, or whatever. So how should we actually write this out? Well, since this is a name, right? Remember, this is going to be what we call it, an existential name. Then let's imagine we write it like this, where we had our name here. So this is going to be our second premise here. We have a name, whatever name that is, right? In this case, it's the C, right? It would be a name is not an A, because the A is the predicate. Blank is not an A, right? And the conclusion here, so what would the conclusion look like? Here, let's go like this. The conclusion, of course, gets written down here. And this would be a blank name. And notice it's the same name, since it's also a C. Blank name is not a B. Right? So that's what that thing looks like. Now, so let's sort of think here for just a moment here. These are our premises, right? We have two premises, and this is our third statement, a line of conclusion. Now, in order for the counterexample to work, this is going to need to be a true statement. This has to be a true statement, but this has to be a false statement. What can we come up with? Let's stick with the example of animals. Let's say we have all cats are animals, right? That's true. All cats are animals, so B here would be animals. So you can see I just fill it in. This is going to be cats, and B here is going to be animals, right? Because I need to make sure it's the same. So now I just need to assign one name here, and it doesn't matter what name it is. Let's imagine here we have George, right? So let's read the statement. What does this say? It says all cats are animals. That's true. George is not a cat. Okay. Now George here is kind of weird because you'd sort of need a specific cat that everyone can recognize. So you can see here, George may not be the best example here because you don't know who George is. I don't know who George is. So let's change this actually. Let's make this Lassie. Um, Everyone I think knows who Lassie is in terms of the show Lassie. Everyone knows that Lassie is a dog, right? And that Lassie is an animal, but everyone also knows that Lassie is not a cat. So that would still make this premise true. So it does matter what name you choose, right? All cats are animals. Lassie is not a cat. Therefore, Lassie is not an animal, right? Now, I know that this is false, but that's because I know who Lassie is. You can see if I use the name of George, that's suddenly a problem, right? So this example here, by using Lassie, does prove invalidity. Oops, that's not how you spell it. It proves that this argument is invalid, but it also reveals something that's important for us, and that's the problem of names. Um, and the question here is, how am I supposed to know which name to use? Well, you have to use, obviously, a name that is universally recognized. And that's very, very difficult. You know what I mean, to do in terms of actually coming up with a counterexample method. Now, these are very simple examples. Imagine, for instance, if we looked at some of the problems we were looking at in a couple of videos previous to this one, which had very, very complicated statement functions. You can see it would get very difficult in order to actually analyze all this stuff and doing in terms of doing counterexamples. And you have to make sure to use something that's universally recognized. I guess if you want, we can do one more problem here that's actually using the counterexample method that's a little bit more complicated in terms of what it would look like. And you're going to see that today's video actually is going to be fairly long here because we're trying to I'm trying to explain this stuff on the video, but when we get to very complicated problems, that's where you're going to have the most trouble. So I'm going to try to do easy and then complicated examples in each statement. So again, do the same thing we've been doing in the last one. Write the problem down and then pause the video and see if you can come up with a counterexample using the counterexample method. The basic way of doing this is going to be the same no matter how long or complicated your problem is or how many premises it has. But obviously it gets more and more difficult. So let's sort of say, what would this sort of thing look like? Well, this really says something like all, right? This is a universal. This whole statement is quantified, so this means I'm going to need an all here. And that basically says all the A's are either B's or C's, right? Because this says if A, then you have B or C. So all of the A's are either B or C, right? That's going to be for that first statement. So let's take a look at the second. The second statement says all the B's are, well, C's and B's, right? So that would say that all B are both C and B, right? That's that second premise. And then the conclusion here would say, therefore, and remember those 3 dots is just the symbol for a conclusion statement. This would say all A or D. Okay, so here is our premises and our conclusion. And again, in order to prove the counterexample method, these need to be true, and this one here has to be false. So let's see what we can come up with here in terms of our counterexample. Now, again, because of the problem of names, they have to be obviously the same. Let's use animals and dogs. Let's imagine I say something like this. All dogs are either sharks or animals. All dogs are either sharks or animals. Now, that seems odd for someone to say that, but you can imagine that's, strictly speaking, true statement. We know, of course, that they're not sharks, but we know they're animals. But this statement is a true statement. It doesn't not denied by the universe. But B here becomes sharks. So this would say all sharks are both. Let's make C animal. Oh, we already did. C is animals and sharks. I'm sorry. Oh, I made a mistake here, didn't I? This should say all B. Oh, this is supposed to be a D. I made a mistake here. So let's erase that. I rewrote the wrong. Yeah, I wrote the problem down wrong on accident here. I apologize. So that should be D, dx. So this would be D. Okay. So all sharks are both animals, and well, what is another thing that a shark is? Shark is an aquatic fish of some sort. So let's say fish, right? All sharks are both animals and fish. That's true. They're both within these categories. Now, what about the conclusion here? That means that all dogs are fish. And that's obviously false. So that means that this argument is invalid. Okay? So that's how you use the counterexample method in these problems. You can see, though, that if the problem gets increasingly complicated, and it will become, this could be very difficult to do on your own, just sort of sitting in your, in your office, imagining this. So what we need here is a second method, method number 2. The finite universe method. The problem with the finite universe method you'll see is that I'm not sure how easier the finite universe method really is. But it's another way to do this, another way to prove invalidity. And you're going to see it's related, right, to the indirect truth table method, which was also a method we had for determining an argument is invalid in propositional logic. So it's related to indirect truth table method. I'll just put indirect truth T here for table, indirect truth table method. So let's sort of go about this. The finite universe method here, it actually can establish the invalidity of any argument that's expressed in terms of a single variable, right? And so what that means is no matter how the universe changes, validity remains so. So what we're going to do here is the finite universe method really consists in terms of shrinking down the universe into one thing. Because if an argument is invalid, right, our idea is that the argument is invalid no matter what universe it exists in, right? No matter the universe. And also think about this, that part of the problem we have with the counterexample method is that I need to find names that are universally recognizable, like Lassie, but some people don't know about those things because the universe is constantly changing, right? So what we need to do is we need to establish a method. We're going to establish a method that looks at shrinking down the universe in order to sort of make the problem manageable, right? Because the ultimate idea here is that an argument is invalid no matter what changes in the universe and no matter what names we can give any of these variables, because the invalidity exists, right? The invalidity of an argument is a structural feature of an argument's form. It's a structural feature of the argument's form. It's not dependent upon the letters, what the letters actually mean, what we symbolize it for in terms of the translation. So it's just a structural feature of the argument's form. So and I'm hoping that I can explain this well, since invalidity doesn't matter what happens in the universe, and we're going to see that what happens if we essentially take the universe here and we shrink it down, right? And we shrink it all the way down until the universe is just one thing. It could be 1, it could be 2 or 3 or however many things in it, right? So, and it seems sort of crazy, but let's imagine, for instance, that we scaled the universe down to just one little dot, and let's call this thing, let's give it a name, and let's call it Abigail. So the whole universe has been shrunk down to Abigail. Now, obviously, we're not positing that that's true, right? This is merely a structural thing, because it would mean that an argument where the whole universe is just one thing, Abigail, if that argument is invalid, it's going to be invalid no matter how many different things exist in that universe. So that's going to make it manageable for us to use the indirect truth table method. Okay, so So what we're going to be basically doing in terms of the finite universe method is the first thing we're going to do is we'll call this the steps for the method. The first thing we're going to do is we're going to have to translate a predicate argument into a finite universe equivalent. Okay, that's the first thing we have to do. Now, the finite universe equivalent means that we're going to determine how many things exist within the universe. Just for now, we're going to start with one. And then if one doesn't work, then you look for two, and then three, and so on and so on and so forth. Okay? So, but the first thing you have to do is you have to translate an argument into a finite universe equivalent. Now, I say equivalent here. The symbol we've used for logical equivalence is 2 colons, right? This is the symbol we use for logical equivalence. Okay, but this symbol doesn't work for us when we use because the logical equivalence refers to statements as they exist within the actual universe, right? Because we're making up our own universes, we're going to use a new symbol, and it's going to look very, very similar. It has a sort of similar meaning, but it's not identical. It's going to be the same 4 dots, but with the C on top. And what this C stands for, right? It stands for the idea that this universe is conditional, right? And it's conditional upon being, namely, whether there only being one thing in the universe, call it Abigail or whatnot. But it's a conditional universe. It's not a real universe, okay? So, so that means, for instance, let's give sort of an example here. And you might say it like this: the exact definition here would be that this thing is the conditional equivalence is such that if the universe were finite in terms of 1, 2, 3, or whatever variables, then the equivalent relationship here, this C double colon thing, is a relation that holds between the finite universe problem and the actual problem, okay? But we're going to see here is that means that anytime we translate something that's a universal claim, right? For instance, an xpx, right? Here, an all state, this is a universal statement function. That's always going to actually turn out to be equivalent with PA here, where A refers to the number of universes, a number of things in the universe. Okay, where A refers to the particular thing. So, for instance, if I said, if I had a universal statement function like this, if I put it into the universal finite equivalent, that means that really there's only PA because the entire universe is just, well, this thing right here. Same thing goes here with the existential, right? If I have a particular statement function, right, well, then what is that going to look like? It's going to be the same, right? Because there's only one thing in the universe, which means that if I say all things are Abigail, that's what this thing says. And if I say that some things are going to be related to Abigail, well, that's this thing as well. So they actually are going to look the same, which consists of giving an existential name. And that's language we borrowed from an earlier video here. Basically, what you're going to do is when you give the conditional logical equivalence here, and that's what we can call this conditional equivalence, that the conditional equivalence here, it actually consists of giving a name in terms, because this would be true in terms of the entire universe, right? If there was some. Now, the question though becomes, what happens if I want to give, if there's one, what if there's 2 things in the universe, right? What if I have 2 things, not just Abigail, but also Bobby, right? What if the universe consists of Abigail and Bobby? Then what are we going to end up with here? Well, that means that the statement that said, right, the statement, a universal statement function of this form in a universe of the size of 2 would say that, well, there's 2 things in the universe, right? There is Abigail, right? And there's Bobby, right? And so that this is where this is symbolized with different names, right? Different statement names, which are these things are the existential names. You give different existential names, and you give two different ones. So if I wanted a statement with three, I would just add on here, right? PC and PD and on and on and on. Where now that there's two of these. Now the rule is though, if you make a statement that's the size of the universe, you're always going to use when you're looking at a universal quantity like this, then you have to use the conjunction. Why? Because this says, right, there's two things in the universe. There's A and there's B. There's Abigail and there's Bobby. But that's not the same as if we use the existential quantifier, right? Because remember, the existential quantifier just says there at least this one exists, right? So what is that statement going to look like? It's what for a universe the size of 2, it's going to be PA or PB. Why is that? Because when you say the sum A or B, right, when you make a particular claim, you're just saying that at least one of those things exist, right? And that's all you're saying. But in a universe the size of 2, right, we still have our A and our B. But the difference here, because we're going to use a disjunction, which means or, either this or this, because the existential here is referring to just one of them, and it doesn't matter which one, right, in the size of the universe. So that's a really important feature here of how to do these problems, is that when you do a universal for a finite universe, make sure to use the conjunction. I think I might, right? You're going to use the conjunction operator. And when you have the existential, you don't use the conjunction, you use the disjunction, right? So if I wanted to add to a universe the size of 3, and it was a universal, it would look like this. PA and PB and PC, right? Now this would be a universe the size of 3, okay? So let me do another example here to show you what it would look like, because one of the things you're going to have to do in order to do this method is you're going to have to practice being able to demonstrate what happens if we have a universal claim that's much more complicated, not much more complicated, but is much more traditional to what we've been looking at. We have something like this, right? How am I going to translate this sort of thing in terms of its conditional finite universe? Well, let's imagine here I have, this basically says all P are X, right? And so let's imagine that I want to create a universe here that, well, let's just write this out. What would this look like here? Let's imagine I want to create a universe of 3, right? So, because we haven't done 3 universes yet. But let's imagine I want to do 3 universes. That means that I'm going to need 3 existential names, but I still have to have this conjunction, right? So what it's going to look like is this, okay? You're going to have P A, then Q A, and because it's a universal, so I'm using the conjunction. And since this is the second universe, it needs to be PB, then QB, right? And I'm running out of room here. Then you would say PC to QC, right? And then I'll close my bracket here. And this statement is the same, except since I have the A, notice I have A and I have B over here combined, right? So these each stand for, this is the first member of the universe, this is the second member of the universe, and this is the third member of the universe, and they're all conjoined with the conjunction again, and that's because of the universal operator here. Okay, so basically notice I just recreated this, but just gave 3 different names and then conjoined them together. So let's do another example here. What if you have an existential statement that looks much more sort of like a traditional, and it says PX and QX, okay? If I want to create the conditional logical equivalence of this, then that means I'm going to create these relationships for a universe of 3, just like I did with this, except instead I'm going to use the disjunction here. And that, again, is because I have an existential operator. So it's going to look like this, right? PA and QA, or PB and QB, or PC, and QC, right? And again, I've just used the disjunction here to combine them together, but the statement function I have here is actually located right here, except I'm just using the existential name. So that's essentially how you translate these things. Now, let's do one more here in terms of translating. What happens if you have to translate something that has multiple quantifiers? It gets very complicated. Well, let's imagine we have this statement. We have x, px, then ex, qx, right? How do we translate this sort of thing? What would count as a logical equivalence here? Well, basically what I'd have to do here is rewrite this entire sequence. Well, here, let me write it. Let me just write it out. It'll help you explain it. Let's imagine we have, let's do a universe of 3 again. Let's stick with the universe of 3 so that way you can at least see what those look like. It would look like this. Now, xpx, that would end up with what? Remember, going back up here, let's see. Right? Remember here that what I need to do is just give it an existential name. Remember what our first one looked like here. Oops. It'd be easier to just scroll down. Right? Right here. Right? Px here. Just turn, here's the px here. Remember, all we did is just gave it into this PA. So that's what the form of it's going to be like. The same thing with the existential. All we do is give it an existential name. So the very first time, these look the same, right? The difference rule is that you use the conjunction for one, the disjunction for the other. So let's go back to this problem here. If I have a px here, then that's going to be, for 3 universes, it's going to be symbolized, well, with just pa, or, I'm sorry, that's universal, so it's a conjunction, and PB and PC, right? And so this thing here, right, is symbolized right here, okay? But notice it's conjoined, so now I have to follow through and move this conditional operator here. And now I have to symbolize this. And how is that going to be symbolized? Well, it's going to be symbolized, well, really the same form, except this time it's going to be QA, or, and I'm using the disjunction here because it's an existential quantifier, or QB or QC, right? Where the existential statement is right here, right? And what I did is I just carried down the conditional statement. So this is how you translate these in terms of its logical equivalence. Let's do one last one, just because they're complicated, and I think it's helpful for you to see how to do these ones, to do these problems, because it's going to require some practice. What happens if we have a really nasty one, right? What if we have this problem? Px, then Qx, or existential quantifier, Rx, and Sx. There wasn't supposed to be a bracket here, so let me erase that. Okay, so let's imagine we have this problem. How are we going to translate this problem? Well, let's see if I can do it just by going straight down here. Again, we're going to try to do the conditional logical equivalence of the finite universe. Let's keep it with the universe of 3, right? So we're going to make a universe of 3. So this is going to look like, right, I have to make this relationship and then conjoin it with 3 of the things that look like this, right? So this thing is going to go here, here, and here, and then I need to bracket them all together. So it's going to look like this. We're going to put PA, then QA, and there's my conjunction. PA, then, I'm sorry, PB, then QB, conjunction, PC, then QC, right? So that's the first one, and then we'll put a bracket in there. And then our disjunction carries down, which is right here. And then now I need to do this. Of course, I need to do 3 statements as well, except instead, I'm going to just use A, B, and C. I'm just going to basically replicate this statement again. So it looks like this. And we'll just start off here. It's going to be R, A, and SA. Or I'm using the disjunction here because this is an existential quantifier, or RB and SB, or, and I'm about to write down here because I'm running out of room, this would be PC and SC, and then the close brackets, okay? And so you have to, yeah, so you end up with this sort of statement here, and then, so that's how you would do it. So notice I carried down my disjunction, but then this whole thing here got moved to the here. It got translated like that, and this whole thing got translated here. But because this was because this was an existential quantifier, right, I used the disjunctions, right? And because this was a universal quantifier, I use conjunctions. Okay, and so that's how you translate these sorts of statements. Now, you can probably almost immediately see that there's going to be sort of a problem here, which is namely, right, just to write this statement, I have to write all of this, right? Some of you are probably thinking, oh my God, that means that this is actually very difficult, and you would not be wrong, right? So let's go back to the steps for the universal. Actually, let's see if I can scroll up and write them out. Let's see here. Oh, I think I ran out of steps here. So let me just scroll down here. Let's just type them in, I think would be the way to do it. Whoop. Okay. So let's just call this the steps for the finite universe method. And I prefer actually to type these out instead, so that way it's totally clear to you, right? The first thing is to translate into the conditional equivalence. Whoops. Equivalent for a finite universe with the number of things equal to n. Okay, so the first thing to do is to translate whatever predicate statement you have into whatever finite universe you're going to build, whether it have 1, 2, 3, or whatever number you're using. Make sure to translate it accordingly. And of course, the thing to remember here is that universals, right, use conjunction, right, and particulars use disjunctions, right, and all variables are given existential names equal to the number of n. Okay, that's the first thing you have to do, right? Now, once you've translated it into its logically equivalent form, what's the next thing you have to do? Well, what we're going to do is we're going to use an indirect truth table, right? Use an indirect truth table. Here, use the indirect truth table method, I should say. Use the indirect truth table method to test for invalidity. Right? Beginning with 1, then 2, then 3, and so on, numbers of n. Okay? So what you're going to do is, as soon as you translate it, then you're going to use the indirect truth table method to test for validity, beginning with first 1, you get 1 member of the universe, then 2 members, 3, and so on and so on and so forth, right? And because the thing is that if you discover that a problem is invalid when there's only 1 member of the universe, then it's invalid for all numbers of universes. But then just because it's not, it may be valid. Here's the problem: is it may be look valid with 1 member, but then maybe it's not with 2 and 3 and so on. We're going to find though that ultimately there is a final amount in terms of how many times you have to test it, and it can be a lot. In fact, that's one of the problems with this method. So, but what I want to do now in the video is, given this method, right, I want to run through a number of problems with you to show you how to do these over and over. And some of you maybe only need to watch maybe one or two of my examples here, but I'm going to do quite a few here just so you can see me using the finite universe method over and over. Now again, I'm not going to do a review in this video about how to use the indirect truth table method. If you need to see that, then you need to go watch the earlier video we posted, so that way you can maybe remind yourself how to do these. I'm going to assume it just because this video is already fairly long. So let's start with this problem here, right? First, it's going to look like this, right? The second, and I'm going to write the premises horizontally instead of vertically in this case. And again, each premise is separated here with a single slash, and then a double slash separates the conclusion. So let's imagine I have this problem, right? So this says that all G are H, and this statement here says that some H exists, and this says therefore there's some G that exists, right? That's how that looks. Now, the first thing I want to do is I want to translate it for a finite universe of 1. That's the first thing I want to do. And then if it's invalid there, then I'll test for invalidity elsewhere. So that means what I need to do is then do the same sort of translation we just did before, which means I need to give each of these existential names and utilize the system. Now, in this one, it's fairly easy because to translate each of these statements into one, it's going to look like this. GA to HA, right? And then this statement here is going to turn into just HA, conclusion, GA, right? Now, in order to test for invalidity in the indirect truth table method, remember, I have to assume here that the conclusion is false and that each of the premises are true, which means I'm going to place a T under each of the main operators for these statements. And this one, there's no operator, so it just goes directly under the variable here. And then the false goes under here. So if GA is false, that means that this is false, right? If HA is true, that means this is true, right? And you can see here, for the conditional, no rules were broken, which means if there's no contradiction exists, then that means my assumption here of invalidity is true, and this argument actually is invalid, right? Now that was a really easy problem because it worked for a universe of 1, right? So that means that I've now proven this argument's invalid. Let's try it harder. You're going to see as I go through these, they're going to progressively get more difficult. So let's take this problem here. JX, then KX, and then I have and then the conclusion I'm looking for here is a universal. Okay, so this says that all of the J's or K's, there exists just at least one J, therefore there exists at least one K. So let's use the finite inverse method here and see if we can come up with something that is conditionally logically equivalent for a universe of 1, because you always want to start with just one universe, because why start with 2? Because obviously it just makes the problem bigger and bigger. So let's try it here. So that means that this is going to be JA then KA, right? There's a universal, so I have a conjunction here with JB then KB. That's the first premise. Now I need to do the same thing here. This ends up with JA or JB, and that or comes from the existential quantifier. And then the conclusion here is a universal, so I have KA and KB. Okay, so now let's start here. Now again, when you do the indirect truth table, start by putting in your assumption of invalidity, which looks like truth under all of the main operators of the premises, and then falsehood under the main operator of the conclusion. Okay, now I usually start with the conclusion here because the thing to remember here is when you're doing the indirect truth table method and you have conjunctions, you can have multiple lines in the table, and that's where it gets sort of unwieldy. But let's imagine, right? This conjunction, in order for the conjunction to be false, just one of these things has to be true, and the other one has to be false. But there's three different ways that could happen, right? This could be false and this could be true, right? And this could be, they could both be false in order for it to be false. So what I'm going to do is I have to check and see if, right, work out the deduction for this first sequence. If it doesn't work out, then I've got to check each of these. But hopefully it'll just work out easy for me. Now, first thing is I have Ka and Kb. There's a Kb here. Kb in this case was false, right? So if Kb was false, remember, then you'd have to sort of ask this question. If Kb was false, then that means that Jb has to be false as well. So in order to make sure that this is true, right? So if this is true, then that means now I know that JB is false. So that means that JA has to be true. So JA is true over here. Now remember, in order for this conjunction to be true, both have to be true. So this one's true. Will this one work out to be true? KA we said was true, right? So true to true is true, which means these two true make this true. So this works out. So since there's no contradiction, right? There's no contradiction. That means that this, my assumption invalidly worked out, and that means that this is invalid. Okay, this is invalid. So that one wasn't difficult. We were able to do that. We did that with the actually, didn't we? We didn't start with the universe of one. I don't know why I did that. I made a mistake here, I think, in terms of my notes, because with this problem works out. If you do this problem with just a universe of one, it actually you won't discover the invalidity, so you have to do it twice. I actually just made a mistake there. But typically we would start by testing a universe of one. If it didn't work, then we would do a universe of two. And that's an example of this. So I sort of made a mistake there, sorry. But let's just keep doing with some other problems. Let's go here and try another problem here. Yeah, let's just start right here. So what about this problem? This is going to look a little more complicated. We have an existential quantifier, hx, then a universal quantifier, so we have compound quantifiers, fx, then gx. The second premise here is ex of fx, and then the conclusion here is going to be ex hx to x of gx. Now the first thing you should notice here is that I have two different quantifiers. I have a universal and a particular here, and the same thing goes here. I have a particular and then I have a universal here. So all of that has to filter down when I do the conditional logical equivalence for the finite universe of one. So let's start with the finite universe of one. What is that going to turn into? That's going to be HA, then FA to GA, and then this is going to be FA because it's a particular, and then the conclusion here is going to be HA to GA. Okay, so let's test this. This was for the universe of one. My apologies on the last time. So that's going to be false, true, and true. So FA's, so now in order for this to, there's only one way a conditional can be false, and that's if the antecedent is true and the consequent is false. So now I have the values of HA, GA, and FA. FA is true, and HA is true, and GA is false. Okay, so true to false is false. So if I have a false here and a false here, this can't be true, right? Right here, there's a contradiction right here. And so if you have the contradiction, then that means you move to a universe of two instead. So, right, so now try, we'll put n plus one universe. Because n here was one universe. Now I want to try it for one more. Let's try a universe of two. Now, in order to keep it expeditious with your time here, I'm just going to write it out because I already have these problems written out for me. So what would the universe for two look like given that other problem? Well, it looks like this. You'd have HA or HB, then FA to GA conjunction, because that was a universal, FB to GB, right? And then I'm going to have my next premise here is going to be either FA or FB. And then my conclusion here, and I'm going to have to write it down here, unfortunately, because I'm running out of room. And you can see that's suddenly that's going to be a sort of practical problem for us, actually. What's going on? So HA or HB, then GA and GB. Okay, so let's start with this problem here, and I'm just going to have to do the conclusion here at the bottom. So the conclusion's false. The premises are each true. So that's going to go there. Oops, that should be an H. Okay, so let's start off here. Where should we start off here? If this is going to be false, then this has to be true, and this has to be false. Okay, you can see here this could be false if this was true and this was false, or if this was false and this was true, or if this was false and this was false. So that means that there are 3 lines here that we have to check. Let's hope this third one works out. Now you can see here, what about this? HA or HB? In order for this to be true, only one of these has to be true, or they can both be true. I'm not sure, because that would be another 3 lines. I'd have to check in conjunction with these lines. You can see it gets like, suddenly there seems like a lot. So before I fill out HA and HB, let's assume that they're going to be the same. One thing we notice is we do have an HA or HB right here. So we'll just put that as true, because if this is going to be true here, it's going to be true here. Okay, but before we can go back to work these out if we have to. But if we go slowly, maybe we'll be able to figure it out. Okay, now GA is going to be true in this universe. So that's true. And GB is false. That's false. Okay, so in order for this one to be true, if this is true, this has to also be true. So if this is true, then this has to be true. And this has to be true. Okay, so if this is going to be true, but my GB here is false, then that means that FB has to also be false. So FB is false, that means suddenly I know that FB is false over here. So if FB is false in this section, then that means that FA has to be true. So that means this is true. So now ask yourself, does it work out? Right? FA, right? The conjunction here, if FA then FG, if both of these things are true, then that is true, which means it works out with this, and this works out. So that means we found our line. Now, the question is, I don't actually need to go through and figure this out, because I know that the disjunction will be true if only one of these is true. I mean, I could find that line very easily. I could just say that this one's going to be true, this one's going to be false. It doesn't actually matter. So you actually don't need to fill out these. You can if you want. Here, we'll do it for you. And that, there you go, is a line that's invalid. So that means that this argument was invalid when we actually looked for a universe the size of 2. Therefore, the argument must be invalid in our own universe, which clearly has more things than 2 in it. Okay, so that's how you can actually prove an argument invalid. So let's do one more here. What happens if we have singular statements mixed in with statement functions? So let's take this down a notch here in terms of what it looks like. You'd have mx and ex in x, and then you have these premises md, therefore nd. Okay, so now let's do the conditional logical equivalence for the finite universe of 1. So what's that's going to look like? Now, what am I supposed to do with these things? We haven't discussed that. Since they already have an existential name, it seems to make sense that, well, let's just start by giving them the existential name of D, whatever the heck that thing is. And so it's going to look like this, right? You're going to end up with MD. Let's assume there's only one thing in the universe, and that's D. Maybe it's David or something. So that's going to be MD and ND, then MD, conclusion ND. Okay, so this is what the logical equivalence is going to look like. Let's run our test. What happens if this is false, this is true, and this is true? Well, we know from here that this has to be true. ND is false. That's a contradiction. So doesn't work with the universe of 2. Let's check with the universe of 1, right? So we have to rewrite the problem again. Now let me leave it on here so you can see what the universe of 2 is going to look like, right? Well, let's just do it like this. It's going to be M, since these are existential quantifiers, we use disjunctions. So that's going to be MD or ME and, right, ND or NE. So we're using DE here, D and E instead of A and B. You can use A and B though, it doesn't matter what letters you use. But you want to keep the letters the same here for the, you just want to carry them down. So it does matter what letters you use, I suppose. So that's going to be MD. Now, since this wasn't a universal, all I do is just carry it back down here, and the conclusion is ND. So notice, right, that these stay the same despite the number of universe, and that's because these are not categorical claims. These are just unbound claims. They have no quantifier, so I don't have to express it over and over. So let's do the truth table. True. And this has to be true. Now, ND, anywhere I see an ND, let's put an F there. Anywhere there's an MD, let's put it true. Okay, now let's see if we can do the truth table here by looking out. So in order for this conjunction to be true, both sides of it have to be true, right? Okay, so in order for both sides of it to be true, you can see I go here. In order for this to be true, what happens if ME was false? Right? It doesn't matter. If true or false, it's going to maintain its truthness under the disjunctive operator, right? And what about over here? Well, if this is false, what happens if any is true? If any is true, then it's maintained, and this argument would be invalid. So in a universe of 2, this argument actually ends up being invalid, whereas in a universe of 1, it worked out. Now that's sort of interesting, actually, isn't it? Because it does mean that we can actually determine under what conditions we might say an argument would be valid, at least in terms of the number of things in the universe, right? But of course, our universe, since ultimately the whole point of doing this is to figure out what would be valid in our universe, this proves it, right? Now, one of the things that's interesting is you can use the finite universe method to prove validity. So you can prove an argument is valid using the finite universe method, but the question is how many universes would you have to check? And the answer is this, because there's a theorem for this, and that is that an argument that does not fail in a universe of 2 to the nth number of members, right, where n, right, designates the number of present predicates, is valid. Okay, so that means if you have a statement that has 2 predicates, then that means you only need to check 2 to the second, which is 4. You only need to check it up to 4 different universes in order to prove it's valid. But obviously, because this is an exponential equation, right? Because it's exponential, that means that if you suddenly have a problem in which there's right? Because think about it here. It would slowly go up very, very quickly. So if you had 10, right, predicates, you would have to check, well over 2,000 times or something. So that in order to prove that it's valid. So that means that for the most part, the finite universe method should only be used to actually determine invalidity, because you would really need a supercomputer, or something to test for validity using the finite universe method. But it does work. It does work, but it would require a lot of work on your part and or probably a supercomputer to do an actual problem that had a lot of different predicates. You'll see though that for us, in terms of your homework, it's not going to be that bad. So let's go here and let me just show you real fast the homework, and then we'll close this video. I know this is a long video today, and thanks for tuning in. But let's sort of show you what it's going to look like here. So proving invalid. Let me scroll down here. And I encourage you to read the explanations given in your textbook. That'll help you as well. But let me just show you one homework problem here. I'm not going to do it because we're running out of time here. Well, sure, let's do one here. Let's do this first problem here, the number 1 here. Let's see if we can do that problem. Let's snipping tool just so you can see. Okay. Okay, so let's do this problem here. So the first thing we're going to have to do is we need to write it out horizontally, right? And we have a universal claim, so that means we're going to have, let's try for a universe of 1. So that's going to be A, then B, A, right? Is the first premise. The second premise here is A, then not CA, right? And that's the second. And then the conclusion here is a universal that says CA, then BA, right? Now, what I'd have to do if I was going to add these is then I start adding my conjunctions, or, well, in this case, my conjunctions afterwards. But let's test this. So if this is false, this would have to be true, and this would have to be true. So let's imagine the only way that a conditional can be false is if this is the case. The antecedent is true, the consequence false. So then I could carry these values into wherever I find a CA. A CA here would be true, and that would make the negation would make it false, right? So if this was going to be maintained as true, then this could be true or false, right? So let's go here to BA. BA is going to be false. So if BA is false and it's a conditional, then that means AA has to be false as well. But if AA is false here, false and false is still true, I found the line. So in a universe of 1, this argument is invalid, right? So that's how you do these sorts of problems. And then if I wanted to test for a universe of 2, then instead I would write this, right? I'd go AA, then BA, conjunction, A, B, then BB, right? And then the second premise here, what would this look like? This is testing for a universe of 2, just so you can see what it looks like, right? It would be AA, then not CA, and AB, then not CB. And then my conclusion here, right, would look like CA, then BA, and CB, then BB. Right, and that would test for a universe of 2 because I would have A's and B's, and then you do 3's and so on and so forth. But let's be happy that it only took me the first universe to do, and that's how you use the finite universe method to prove validity, but we're mainly using it to prove the invalidity of arguments. Okay, thank you guys for watching. I want you to know that there's more things that come after this in terms of predicate logic, but I'm going to be ending our series here with this video. So thank you guys for watching. I'll be posting more videos as we go through. I appreciate your guys' comments and watching the channel. So thanks a lot for watching, and I'll see you guys online. Bye.